I like to record these lessons and I will post them into Canvas in case you happen to want to review something from my lecture, say in a couple of weeks, or if you happen perish the thought to miss class, the lecture recording of this will show up on Canvas. You would be able to watch that later. So what I usually like to do at the start of class, guys, is put up a quick review or recap of what we just talked about in the previous class. In this case, the recap I've put up here is just a summary of the notes from, yes?
The right roster.
Is this not the right roster? Nobody has their name on here? Okay, I must have, you know what I bet I did? I bet I brought the wrong one. I will go down during the break and grab the right one. We'll try. I screwed up on which roster I brought. So I'll try that again later. Yeah, sorry. Thank you. I usually like to start with a quick summary of what was in the previous class. In this case, I've made a little table for you. And we're going to be expanding this table even more. It's not a bad idea to pull out an iPhone and take a picture of it, or you can write it down, whatever way you want to do things. But sometimes people don't write down these recaps, and then halfway through the semester, they kind of wish that they had been, because they're just nice summaries of what we had covered up until this point, and it kind of gives you a quick overview. So in the videos last week, we were talking mostly, I'll get out of the way. We were talking mostly about solving differential equations. And in the first homework assignment that you did on Friday, we didn't know how to solve anything. We didn't have any techniques to solving differential equations. So I gave you that position, velocity, acceleration example because, well, everybody can do integrals basically. But it was only in the later videos that we had last week that I started actually talking about how to solve certain types of differential equations. And there are two types that we have covered up until now. And they are the separable equations and the linear equations. These are from sections 1.4 and 1.6 of our book. Those are the sections on tonight's homework assignment. And let me just quickly review these. And by the way, we're going to be reviewing them with some examples today as well. Separable equations is exactly what the name says, guys. You can separate the two variables, the x and the y in this notation, onto opposite sides of the equal sign. Okay, so if you have a separable differential equation, you should be able to get all of the x's onto one side and all of the y's onto the other side. But the harder part of that is just the algebra that goes into separating it. That can sometimes be the hardest part. You do have to algebraically separate it. In order to solve a separable differential equation, you simply separate it and then integrate on both sides. If possible, once you've done that, it's nice to solve for the unknown function, which is usually what y represents. So you try to do that if possible, solve this for y. Sometimes it's not possible, in which case you can just give an implicit solution. A great application of separable differential equations where it comes up in a real world scenario is something I talked about last week, the Newton's law of cooling. And this is a differential equation that looks like dt, the rate of change of the temperature with respect to time. And it is equal to negative a proportionality constant k times the difference between the temperature of the object, which is this unknown function, and the temperature of the medium that the object is sitting in. That's the T sub m, right? So I wrote this down in the videos last week, and we also solved it last week. We actually have a solution for it, which you can then use for application problems, right? So those are the separable differential equations. There's not a lot to memorize here. You just have to go through the motions of algebraically extracting the variables on the opposite sides of the equal sign and then integrate both sides. Yeah, that's the technique there. Stop me if there's any questions, guys, as we're going along here. Now, not every differential equation is separable, so we have to go beyond that. And the next thing I talked about in one of the later videos are the linear differential equations. And a linear differential equation has this form right here, this is one you're going to want to memorize, right? Y prime plus P of X times Y equals Q of X, right? This is the form of a first order linear differential equation. If you see a differential equation like that, and again, you might have to do some manipulation first. You potentially could have to do some algebra to get it into that form. But if you see a first order linear differential equation and it looks like this form, the way that you solve it is by using something called an integrating factor. It's called an integrating factor I of X. And I derived all of this last week, so I won't go through the details again. But this is a formula. I'm going to put a box around this one. This is one you will want to know. The integrating factor is e raised to the power of the integral of p of x dx. Right. So you have to calculate that first. This p of x is just the p of x that you already identified in the linear form of the equation here. Okay? And then once you've done that, I did a whole derivation and so on. You don't need to remember the whole derivation, but the upshot of it is that you end up here with the derivative of the integrating factor times the unknown function y equal to q of x times I. From here, you can solve for y. I won't write it into the notes here. It's simply a matter of integrating both sides, and then ultimately you'll have to divide by I in order to isolate that y. So it's just a couple of manipulations from there. So that's how it works. We're going to practice this again today. A nice application of it that I had given in the notes last week is those the problem of the chemical sitting in the tank or the beaker or whatever it is. And we want to know, well, what's the amount of chemical at time t in that beaker? And we can set that up as a first order linear differential equation. And of course, it's a word problem, so you have to be given some information here. I won't review what all of these constants are, but that's something pretty much just a plug-in kind of thing from the word problems. Okay, so what I tried to do here, guys, is kind of make a nice table, the two types of differential equations, what they look like, a summary of how you're going to solve them, and then at least one real world place where you might find these equations showing up. These are the two most commonly encountered differential equations in the real world, right? So if you know how to solve separable and linear differential equations, you have made great headway on being able to solve differential equations in engineering and science all over the place. These are the two types that come up the most often. Okay, that's why we covered them first. That's why I want everybody to know how to do them, because these are the ones that you're going to see in your real world experience. Okay, are there any questions on the kind of the summary there so far? Please.
For the linear equations,
yes,
techniques to solve those equations that you have boxed.
Yeah,
we're not actually using those equations to solve our problems, but this is like how we get to the equation that we use to solve problems.
Actually, you do need to do both of these equations. Like you will need to calculate the integrating factor to solve your linear equation, and then you will need to ultimately write this down as the step that then allows you to solve for y. So yeah, these two boxes are actually things that you will need to know, and we'll see that as we practice it again. Yeah, good point. Any other questions? So far, so good. Everybody with me? Okay. So these are not the only two types of differential equations that show up in the real world. There are many others. In fact, there are countless others, right? But as you go deeper and deeper and deeper, the amount of application that you find in the differential equations kind of goes less and less and less. We could spend 15 weeks of me just giving you a new type of differential equation, and then here's how to solve it. Here's another equation. Here's how to solve it. Here's another, and you guys will be bored to tears and really not feeling very good about it. Just going to be memorizing stuff for 15 weeks that probably would forget later. It's not what I'm interested in, right? I do want to talk about some of the overriding techniques, though, that are really helpful in solving other kinds of differential equations. And I'm only going to talk right now about one very important technique. It's actually a technique that you use in calculus to solve integrals. So this will not be anything that seems too far crazy, I don't think. It's in section 1.8, which is, by the way, the last section of chapter 1 that we're going to cover. So it is called change of variables. It's called change of variables. I'd like to cover this section to start off today's class. And the idea here is that maybe you have a differential equation that's not separable and not linear, but maybe we can do a change of variables on it to convert it back into a separable or linear equation. That's going to be the idea here, okay? And I'm going to give you 2 examples of this. I'm going to label them with A. So I'll write down what these are first, and then I will go back and talk about each of them. The first one, which is A, is going to be something called a Bernoulli differential equation. Okay, so I'll come back in a second and I'll explain what that is. The second one, which is B, is going to be a homogeneous differential equation of degree 0. So we are just about ready to double the number of kinds of differential equations that we know how to solve. Coming into this week, we should have known these 2. By the end of today, we're going to know 2 more. Okay, and the trick here is going to be to take the Bernoulli equation and apply some kind of a change of variables to it, which I'll explain in a minute, and it will convert it into a linear one. And of course, linear ones we already know how to solve, right? If we followed my videos anyway, we know how to solve them. And then the homogeneous differential equations of degree 0, those are always going to become separable. So I'm just going to talk through both of these applications here, but really the crux of this, like why am I covering this, is I want to show you the technique. I want you to appreciate that you can use a change of variables technique in math to take a hard equation to solve and convert it into something that is actually now familiar again, right? That's the idea. And you did this in calculus with integrals. You had some problem that was too hard to integrate, so you did a U substitution, right? It was like the first technique you learned. Well, you're changing variables, right, to take a hard integral and use a U substitution to convert it into an easy integral. It's kind of that philosophy here. Yeah. Okay, so let's get into it. Let me talk about the Bernoulli equations first. That's part A. So I'll go back to A here, and let's just run through how this works. A Bernoulli differential equation, first of all, I have to explain what that is. I will usually try to underline the word that I am explaining or defining. So this is a differential equation, DE stands for differential equation, of the form. Okay, and now I'm going to write down the form of this Bernoulli differential equation. Y prime plus P of X times Y. I'll stop right there for a second. What I've written up here so far is exactly the same as the left side of a linear equation. So it's going to be very similar to a linear equation. But on the right side, we will have Q of X times Y to the N. And I'm going to put this in a box because this is one you will want to learn. This is a Bernoulli differential equation. It's not quite linear because a linear equation should not have powers of y in it. And so if that wasn't there, then we would have had our linear equation from earlier, you see? So this is very close to being linear, but it's no longer linear. The idea is going to be to try to convert it back into a linear equation by doing a change of variables. So there's a trick to this, and I'm not going to go through the motivation of the trick or anything. I'm just going to tell you what this change of variables is. So to solve this, let's just come up here. To solve this, we use the change of variables. So now I'm going to write down what the change of variables is. And again, I'm kind of pulling this out of the sky right now. I'm not really motivating it. I'm just going to write down, this is what works. Trust me, I wasn't the one that figured this out. Somebody way smarter than me and way before I was ever here figured out that we can use a change of variables on this Bernoulli equation. And here it is. U equals y to the power of 1 minus n. So this is what we need to have. Guys, every time I put something in a box like this, it's probably something that's going to be good to make notes of and to try to learn. So this is going to be the change of variables. If we implement this change of variables, so everywhere I see a y in my Bernoulli equation, I'm going to somehow use this change of variables to write it in terms of u instead of y. Okay. And also there's a y prime, so we would have to deal with the derivative of y, which would be in terms of the derivative of u. I actually am not going to show the full derivation of this. I'm going to say see video. So I made a video that shows what happens when you take the Bernoulli equation and you implement this change of variables. And I showed how it becomes linear. I thought it was going to be some big, massive, incredible video. It turned out it was 3 minutes. It's only a 3-minute video, but I think I'm going to save it. Sorry about that. I think I'm going to save it. It's not critical to this lecture, so I will go ahead and omit this little step for now. I normally don't do that. You will normally see me deriving and explaining every little thing I do. But in this case, I'm going to write down another differential equation, which is the new differential equation that we get when we apply this change of variables. And here it is, guys. U prime plus the quantity 1 minus n times p of x times u equals the quantity 1 minus n times q of x. And again, I'm putting this in a box, and probably so should you. These 3 boxes on this middle board are really the ones you need to know for this section. Okay? Let's take a look at this, try to help you see what's happened here. The 1 minus n is just a number. Remember, the n is some power of y that was in the original Bernoulli equation. We can identify that just glancing at it, right? Just looking at the equation, we will know what n is, and it is just a number. So 1 minus n here is just a number. The p of x that we had in our original Bernoulli equation is just being tweaked by this 1 minus n scalar. And on the right-hand side, the q of x is still there as well with this scalar, this number 1 minus n in front of it. But what you do not see on the right-hand side is u to a power. The y to the power that was originally here that made it Bernoulli is gone. It's gone, which actually tells me that this equation is now linear. This is linear. It has become linear as I sort of advertised. The Bernoulli equation becomes linear when I do this change of variables. Again, to really see that magic, you have to spend 3 minutes of your time and watch the video. Where is this video? Maybe I'll fire up the computer and show you in a little while. It's in Canvas. It's in Canvas. It's totally optional, but I've got a library of some videos that are there that I probably at some point should pull up and show you. Anyway, that's it. That's the whole discussion about Bernoulli differential equations. I would like to do an example. And by the way, in doing an example, it'll help us to review linear differential equations also, right? Because we ultimately have to solve the linear equation that shows up here. Okay? Everybody good so far? Let's try an example. I'll put the example here. EX, whenever you see me write EX, it just stands for example. It's the way I like to notate my examples. So let's try to solve this equation, guys. Y prime plus 2x divided by 1 plus x squared times y equals xy squared. Okay. So let's try to solve this. When I say solve the equation, I mean I would like to find y. And I would like to find the general solution for y. Okay, so there will be some constants in the solution. It's a general solution that we're looking for here. Okay, so let's just take a look at it. Does it look like the Bernoulli form? I've got y prime plus, now here's p of x, guys. This is the p of x part, the 2x divided by 1 plus x squared. That's being multiplied by y. And then on the other side of the equation, the q of x is just this x right here. And sure enough, we have a power of y on the right side, yeah? So this is, just to start my solution here, SOLN is my abbreviation for solution. This is Bernoulli. And it's always good to just identify that first so we know what kind of an equation we have. And it is Bernoulli with, what is the value of n for this Bernoulli equation? The n is the power of y here, so we just look at our problem on the right-hand side, y to the squared power, that means n is 2. Okay, so this is Bernoulli with n equals 2. Let's take a look at our change of variables. The change of variables is, so I'll just write it this way, we have u equals y to the 1 minus 2. This n is 2, and that's actually just y to the negative 1 power, which I'm just going to write as 1 over y. So the u is just the reciprocal of y. They're just reciprocals of each other. So far, so good? Now, let's write down the new linear differential equation that we should get. If you trust me that I'm not lying to you about what's in my video, and that this really is the new differential equation, it should be linear. Let's write it down. U prime plus, now 1 minus n, that would be 1 minus 2, right? So that's actually just negative 1. So actually this plus should actually have been written as now a minus 2x over 1 plus x squared times u. And this should be equal to, take a look at the right side. The right side of what I should end up with is 1 minus 2. That's negative of whatever the original q of x was. The original q of x was x. So we would now have minus of that. So that we end up here with minus x. This is a linear differential equation for u. Good enough?
It's not too bad, actually.
That's not so bad. It's not so bad. Now, we're not done, of course. We have to still solve this equation. That's why I said we're going to be reviewing last week's videos a little bit, because we now need to remember how to solve this linear differential equation. This says, okay, I got to use an integrating factor and go from there. So let's come up here to do the last part of it, guys. The integrating factor. Okay, so this is a good review of last week. In case anybody didn't feel so good about the video last week, we're going to do it right in front of your eyes right now. The integrating factor, that's the I of x. This is e raised to the power of the integral of, now here we have to be careful. It says the integral of p of x dx, but I want to be clear that it's the new p of x, not the p of x from the original problem, but the new p of x that we have here. And in this case, that means that this minus, right, notice the original problem had a plus. Now it has become a minus. That minus is part of the p of x. So I actually need to have that in there. Minus 2x over 1 plus x squared dx. That is my integrating factor. E to the integral of this p of x from down here. Okay, now to do this integral, I'm going to pull out the minus, if that's all right. And then if you kind of just ignore the minus sign, the rest of what you see there is 2x divided by 1 plus x squared. You folks know how to integrate that maybe?
U sub.
A u substitution, absolutely. We can do a u substitution where the u is the denominator, okay? right? So I can do this integral by letting u equal 1 plus x squared. The du would be 2x of dx, right? I pulled out the minus just to get it out of the way. The minus is here, but then I'm integrating 1 over u du, which is
ln of u.
the ln of u. Absolutely right. The ln of u, I'm going to go ahead and put what u was back in there again. And so it's negative of the ln of 1 plus x squared. Now, do I need to put a plus c? You remember when you took calculus, your antiderivatives in calculus, your instructor was probably always harping on adding a plus c to the end of your antiderivatives. Do we need to do that here?
Oh, yes.
Well,
you showed it.
I buried this in my video last week, so it might have been easy to lose this point. Guys, we only need to find one acceptable integrating factor. We don't need to find like the general formula for all of them. So we can actually go ahead and choose the c to be 0, the plus c to be 0, so we don't even have to write it down. It's just going to make our life easier to not even write it down. So I'm just going to leave it without the plus c. Also, the one other thing I should mention is when you integrate 1 over u du, technically you get the natural log of the absolute value of u. In this case, you notice again, I did not use absolute value bars around 1 plus x squared. Everybody know why? Because it's already positive to begin with, right? Is take the absolute value of something that's positive, you don't really need to do anything. So I just write down what it is right there. So this is it. However, I'm going to want to clean this up. I would love to cancel the e with the ln here. Can I just cancel them and write down negative of 1 plus x squared? Ooh, I have to be careful. Properties of logarithms have to come into play here. So this is the ln, e to the ln of the negative first power of 1 plus x squared. And so that just becomes, now I can cancel, and I just get 1 over 1 plus x squared. That is your integrating factor, okay?
Oh, that's the logarithm property?
Yeah, that's a property. So one of the properties of logarithms is that if you take the log of some power of x, the power comes down in front. So if I had a p-value of -1, right, it gets shoved upstairs as an exponent, just as I've shown there. Yeah, that's right. So that's one of the properties of logarithms that is quite important. Most of this over here is just calculus and algebra, but it is necessary to do it here. Is everybody all right with that? Question or?
Yeah.
Please, yeah, go ahead. Go ahead.
The formula, the
This part?
change of variable, yeah.
Okay, this thing right here. This thing right here, I actually have not used it yet.
Oh.
I have not actually used it yet at all. That's a very good point. I should have mentioned that. I wrote it down right here just so I wouldn't forget about it. But this actual change of variables has not been used yet. It's going to be used, but we're just not there yet. I kind of swept it under the rug how this change of variables leads to this linear equation. So again, that's kind of in this little 3-minute video as to how that comes out. But we just went straight to the linear differential equation. And at this moment, I'm actually just solving for u from this linear differential equation. It's easy to get lost in the process here, so I appreciate the questions to kind of make sure we stay grounded and stay focused on where exactly we are. Yeah, we are in the process right now of solving this linear differential equation. I have found the integrating factor. Once I've done that, let's remember, we use the integrating factor to obtain this expression right here. I'd like to write that down for you. It would be the derivative of some product on the left side. What do we have there? Well, my integrating factor is 1 over 1 plus x squared. And my unknown function at this moment in time is actually u. Right. Okay. And then on the other side of the equation, let's just check it out over here. Q of x times I. So the q of x, keep in mind, it's the new q of x, this one, negative x times the I, which is 1/1 plus x squared. I'll just write it like that. This is what we end up with, and we are going to solve for u just as we did in the videos last week. Once we get to this step, we have to integrate both sides. So let's do that. Let's integrate on both sides. When we do that on the left side, we just get rid of the derivative, right? Derivatives and integrals are opposites of each other. So we get rid of that derivative. Yes. Can I what?
Slow down.
Slow down a little bit. Okay. I will try. Get excited. Thank you. Jeez. I get excited.
I was gonna point out, so basically when we're given a Bernoulli problem, we're gonna use the integrated factor, right? And by using that, we want to be able to obtain the bottom,
This one.
the bottom right, and then go from there.
Yeah, and in the videos last week is where I actually did this. I showed how we use this integrating factor to obtain this one.
Yeah, I think it's just like, at least for me, but in person, I
Yeah.
think it's like I soak it in more.
Super, yeah. So this is ultimately we're using that process from section 1.6 to take the integrating factor and obtain this derivative of the product of the integrating factor with our unknown function. At this moment, our unknown function is no longer y, it is u, because this is the equation we're solving. Everybody else with me? Are so good? So the left side, what I've got here on the left side, guys, is just the result of integrating the derivative. You see that? This is the derivative of a product. If I integrate it, I get rid of the derivative and I just am left with what was inside. I also have to integrate the other side. So I have to integrate negative x divided by 1 plus x squared. Just like so. So I put an integral sign in front of that, and I'm going to do that integral just now. Okay? Actually, this integral is not all that different than the one we just did a minute ago right up here. There's no factor of 2 here, but I can put a factor of 2 there. Right? I can put a 2 right there, can't I? As long as I put a 1/2 in front. You've seen that trick before, right? So the 1/2 is actually going to show up out in front of the integral. And I still have that minus sign, just like I did earlier. There's a minus there. This minus right here, I'm just pulling it out of the integral. So the minus comes out, the 1/2 comes out, and now I'm just integrating the same du over u. So I get the ln of, I'll ignore the absolute value bars, don't really need them right now. So I just get the ln of u. This time, however, the one thing that's a little bit different here is this time I do need to add my plus c on that antiderivative. I didn't do that when I was solving my integrating factor, but I have to do it here because I'm in the process of getting the general solution to the differential equation. Okay. So we're almost there. I can solve for u. Let's solve for u right here. Let's do it. So what is u equal to? This is the whole objective, is to solve for u. I've got 1/x² times u is equal to the far right hand side. Well, to isolate the u, I just need to multiply that 1 plus x² across. So I'll end up with 1 plus x² and times the quantity of negative 1/2 of the ln of 1 plus x² plus c. Yeah, just like that.
What about the u that we have on the?
In the box there?
Yeah.
I'm about to come back to that. Yeah, so this is the same question that I was mentioning a minute ago. I wrote down this change of variables, but I didn't really use it yet. I didn't use it yet because all of the work over here is just to solve for u in this linear differential equation. But now, guys, here's my question for you. Is this the final answer? No, because the original problem has an unknown function of y, not u. Right? So I've solved for u, but what I'm looking for is y. And the question is, how do I go from u to y? This should answer your question and your question. It's this box right here. U is the reciprocal of y in this case. So they are just absolutely flipped over versions of each other. So what is y? Y is 1 over u.
The whole
Y
thing.
is 1 over the whole thing. 1 plus x squared times the quantity of -1/2 of the ln of 1 plus x squared plus c. That is the final answer. That is the final answer. Yeah, that's it. And it is a general solution because there is a c as part of that solution. This is not just one solution, guys. This is an infinite family of solutions depending on what c is. C could be equal to 1, it could be equal to 2, it could be equal to pi, it could be equal to 5 billion. It's a constant that could be any number. If you wanted to solve for c, somebody would have to give you an initial value. They would have to tell you, oh, y of 0 is equal to whatever. And then you could solve for c. Okay, that is the Bernoulli differential equation. A lot of the work is just solving the linear equation for u. And then just don't forget at the end, once you have solved for u, to use this change of variables right here to go back to y. All right, how am I doing? Question?
So if we had like on the Q of X, if we had a higher like order of exponentiation, right?
Like this x was like.
No, like on the Y.
Oh, on the
If
y.
we had like a 5 or whatever,
Yeah.
it'd be the same thing.
Same
Just
thing. Yeah, it would just be u equals y to the 1 minus 5. And so then that would be 1 over y to the 4th instead. Yeah, that'd be the same thing. It'd be the same thing. Absolutely. Okay. Other questions on this one? So far, so good on the time. I think I'm going to take just a few more minutes and talk about the item B in my list. So this is an example of converting a Bernoulli equation into a linear one by doing a change of variables. I would like to show you one more example of this change of variables technique. So I think to do that, I'm going to go ahead and erase here, if that's okay. Everybody got it down? All right, fantastic. Yeah, I started recording my videos when I was teaching during COVID. That was really the thing I had to do. And when I came back from COVID, I stopped recording the videos, and the students said, well, why did you do that? We like having the videos. So yeah, if you need to rewatch anything, or if you miss any notes or anything like that, I will put these up for you. So you'll have a chance to look at it. It's not the greatest quality. You should definitely be here in person. Because otherwise you're going to be squinting at the quality of the video. Yeah.
I was just gonna say, just because I'm really into photography and like video,
Uh-huh.
how come you don't use the back camera?
I should. I'll talk to you about that after class.
Okay.
Okay, sounds good. Yeah, so let's do B, homogeneous differential equations of degree 0. Okay, this one's a little easier. This one's a little easier. The Bernoulli one is really pretty involved. Let me make the definition here of what this is. So a homogeneous differential equation of degree 0. This has the form. So a homogeneous differential equation of degree 0 has the form y prime equals. So this is very different than the Bernoulli equation. We've isolated the y prime, and on the right-hand side, we're going to have f of x and y. Now, that just means there's some function here, some expression that involves x and y, and technically it could be anything on the right-hand side that has x's and y's in it. But there is one constraint, there is one condition here, and that is where, I'm going to write this down for you guys. This is where f of x and y, it can't just be any old thing. The right-hand side cannot just be anything. After all, not every equation is going to be homogeneous of degree zero. So on the right-hand side, you have some function involving the x and the y, but it has a special property. And that special property is that if you were to go back and replace every x with xt, now this t is nothing magical. It's just like a variable that I'm introducing and I'm attaching it to the x. So everywhere I have an x, I can imagine having xt. And everywhere I have a y, I'm also going to imagine having yt. This is what it means to be homogeneous of degree zero. If you take your function and you replace all of the x's with xt, and you replace all of the y's with yt, you find out actually that all of those t's completely cancel back out, and it's just equal to what you started with. That's what this is saying. This is saying you take your function, if you replace the x with xt, and you replace the y with yt, well, all the t's just cancel out, and you really just have the same f of x and y again. This is an equal sign. That's what we're saying. That's what this is saying. Let me show you an example before we actually solve a differential equation. Let me show you an example of this homogeneous of degree zero concept, right? So for example, f of x and y, if we made it equal to something like x divided by y minus 1. Okay, so I'm not solving anything right now. I just want to understand this definition over here, right? So if this was my f of x and y, then the question is, what would f of xt, yt be? And again, t is just some mysterious parameter that I'm inserting into the formula. So everywhere I see an x, I'm going to change it to xt. Everywhere I see a y, I'm going to change it to yt. Everything else I just leave as is. So we just get xt divided by yt minus 1. Now my question is, is that equal to the original f of x and y again? Can I cancel these t's? I see many people trying to do it. This is one of those algebra things that you cannot do, right? You cannot cancel these t's because the minus 1 does not have a factor of t associated with it. This is not equal to the original function. This is not homogeneous of degree zero right now. Okay, so f is not homogeneous of degree zero. It will not be. But just so we understand the definition, let me write down one more example. Again, we're not solving any differential equations yet. I'm just trying to make sure we understand what this homogeneous of degree zero thing means. Is everybody okay with that first example? It's not homogeneous of degree zero because you cannot just cancel the t's, right? For this second example, let's take f of x and y, f of x comma y, let's take it to be equal to x squared minus xy plus 2y squared, all divided by 2x squared plus 3y squared. So I'm going to make another example. This is also what they call a rational function. It's a fraction of two polynomial expressions. And I would like to just figure out whether this would be homogeneous of degree zero. So let's, I'm going to need to go to a new line here. This one's a little bit longer, but let's write down, maybe down here, what is f of xt comma yt? See if we can make heads or tails of this one. So in this case, all I'm going to do, guys, everywhere I see an x, I'm going to replace it with xt. Everywhere I see a y, I'm going to replace it with yt. So the x squared becomes xt squared. And then I have minus, the x becomes xt, the y becomes yt, and then plus 2 times, and this is going to be the quantity of yt squared. Sorry, I'm kind of, hopefully everybody can read that. I've had to kind of compress my writing a little bit. The denominator, I have to do the same thing. Everywhere I see an x, I'm going to change it to xt. So it becomes 2 times the quantity of xt squared, and then plus 3 times the quantity of yt squared. And the question of the hour is, will all of these t's cancel back out if we do the algebra? If we try to simplify that. Now, in the first example, when we tried to simplify it, we couldn't make the original f of x and y come back again. But the question is here, is it going to be the same result, or will we be able to do it? What do you guys think? Do you think I'll be able to cancel all the t's and make them all disappear?
Yeah.
If you look term by term on both the top and the bottom, every one of these terms, right, has a t squared. You see that? Here's a t squared, here's a t times t, here's a t squared. Same thing on the bottom, t squared everywhere. In fact, let's write this down. If I continue here, guys, in the numerator, I can factor a t squared out of all of it, yeah? Out of every single term, I can factor a t squared. It's going to look like that. If I factor just on the numerator, I take a t squared out of everything. And actually in the denominator, I will also be able to factor out a t squared from both of the denominator terms as well. Yeah, I can do that on the top and on the bottom. And so this is what we would end up with, guys. And these t squareds do cancel. And if we look at what we are left with after we've canceled them, it should be the same thing we started with, the original f of x and y. Yeah, so this is equal to f of x and y. That checks out. That's actually exactly right. Yeah, so in this example, f is homogeneous of degree 0. Yeah. What's really going on? Actually, what's really going on is that if you look at the original function, it's completely balanced. There's 2 powers of the x's and y's on every term on upstairs and downstairs. It's completely balanced on the top and on the bottom. Does everybody kind of see that? The t is what's measuring that. Those t's that we're attaching to the x's and y's is measuring, are the terms balanced or not? How much weight do each of those terms have? In this case, everything is totally balanced. This is degree 2, degree 2, degree 2, degree 2, degree 2. Upstairs and downstairs. The original problem was not that way because there was a term that had sort of no weight at all compared to the x and the y. It didn't cancel out. So that's the difference. That's the difference there. Now, I said that if our differential equation is homogeneous of degree 0, we should be able to solve it by doing a change of variables. So I'm going to write down the change of variables, and then we'll do one example, and then I think we'll take our little 10-minute break. So this will pretty much wrap this up. But for these homogeneous of degree 0 differential equations, it's actually a little easier than the Bernoulli one. So for this type of differential equation, we can use the change of variables that I'm about to write down. So for any homogeneous differential equation of degree 0, we can use the following change of variables. So let's write it down here together. basically, here's the way it's going to look. And again, this is being pulled out of the sky a little bit. Like I'm not really showing you where this is coming from. But the change of variables is going to be y equals x times v. I'm just choosing not to use a u again. We used u for the Bernoulli equations, and I just didn't want to use the same letter again. So I'm using a v for the change of variables this time. Everywhere I see a y, I'm going to change it to x times v. And I might as well, so here's the form of our differential equation, guys. Y prime equals f of x and y. I might as well tell you what y prime is because we're going to need that. Let's just do that now. If y is equal to x times v, then I think we all know the product rule. To take the derivative of this to get y prime, I would just get x times v prime plus v times 1. And so it would just be that. X v prime plus v. That would be the y prime. Okay. And since I don't have like an explicit form of what this f of x and y looks like, I can't tell you exactly what magic is going to happen when I use this change of variables, except to say that when you implement this, you will always get, as I said earlier, in this case, it will always result in a separable differential equation. And again, that's something we talked about in the videos last week. Separable differential equations. Okay, so let's do one example of this and then we'll take a little break, okay? Is everybody so far so good? Let's do, I think I have room here. This is not going to be quite as tedious as the first example, so I think this will go pretty quickly. So here's my example, guys. Let's solve y prime equals y over x plus the square root of 16x squared minus y squared all over x. So let's take that guy. Now, we shouldn't jump the gun and just say immediately, oh, that's homogeneous of degree 0, because we've learned other things. We should really go through a process right now. Just say, is this separable? Is it linear? Is it Bernoulli? Could be any of them. Okay? You're going to have to be able to decide that. If I look at this, I don't think I can separate an x from a y when it's trapped under a square root with a minus sign, right? You're not going to be able to separate this one out and get all of the x's on one side and all of the y's on the other side. So no chance of that. It's also definitely not linear, because a linear differential equation, as we've talked about before, should not have a y squared in it. That's y times y. That's not allowed on a linear equation. If it's going to be linear, it has to look like this. Okay, well, that doesn't look anything like it, right? So this is not a linear equation. It's not even close to the right form. And actually, the Bernoulli equation would have to be basically this, but with a y to the n tacked on the right-hand side, and that's not even close to what we see over here. Guys, by process of elimination, this is not separable. It is not linear. It is not Bernoulli. So it better be something else. And it is actually homogeneous. If you take this right-hand side as your f of x and y, and you attach t's to every x and every y on the right-hand side, you can check it. I don't think I'm going to do it now, but you can check it that the t's would all cancel, right? If I change the y to yt and the x to xt, they're going to cancel right there. Yeah. If I do the same thing in here I have to put a t squared underneath the radical and then factor it out of the radical, but that will be a factor of t that cancels the t that would be on the bottom. So kind of waving my hands right now. But if you wrote it all out, the algebra of that, you would see that the t's would cancel, and it sure is homogeneous of degree 0, right? So this is homogeneous of degree 0. Absolutely true. Okay, So if we kind of are on board with that, then we've got our prescription here, like what we're supposed to do. Yeah, so I've got my change of variables. I'm just gonna write it down again. So y is equal to xv. We'll just put this as part of the solution here. Y is equal to xv and y prime is equal to xv prime plus v. Just kind of recopying that again. Again, this is just coming out of the sky, just kind of trusting me that this is gonna work out. Question? Why it's not Bernoulli? Yeah, so if it was gonna be Bernoulli, that's a good question. That's a really good question. If it was gonna be Bernoulli, then it would have to be possible to write it so that it looks like this form right here. Okay, so if we remember from a little earlier today, the Bernoulli form looks like this. And I don't really see how to, like, I see a power of y here, but it's not like outside by itself. It's stuck under this square root with a minus in front of it. So just from an algebra perspective, you can't really reinvent it to look like the form of a Bernoulli. That make sense? Yeah, but that's a really good question. We shouldn't just jump to conclusions about these things. We should look, is it separable? Is it linear? Is it Bernoulli? Those are good things to be asking.
What
Yes,
if,
please.
what if you had like a, because I agree with what you're saying, but what if you had a y to the right side just multiplying, like y to the y squared?
Like over here,
Yeah, like would that be considered Bernoulli then?
this would not be considered Bernoulli because the thing that the y squared is multiplied by, trapping myself in the corner. The thing that the y squared is multiplied by has to be only a function of x. And there's stuff here that has both x's and y's in it, so it actually wouldn't work.
Okay.
So it's a good thing to think about. But yeah, in this case, that doesn't work either. Yeah, please.
Wait, so it would only be like, only one side has to be like X purely and the other has to be like Y purely in order for that
To be Bernoulli?
Yeah.
You have to have basically this form right here on the right-hand side. So you have to have a power of y that's been totally extracted from some function of x.
Yeah, 'cause
Yeah.
when I was reading the textbook.
Yeah.
Okay, they would all say like one side is this factor only, the other side.
Very, very true. Yeah. I mean, Bernoulli equations, they're very specific in their form. So it's not gonna be the end all be all that everything is Bernoulli, right? Not a lot of differential equations will be, but sometimes they will. Yeah, okay. Okay, guys, so what we need to do now with this change of variables is plug it all into the problem. On the left side, I have y prime. I'm gonna change that to, so let's do the plug-in part here, guys. I think I have enough room to do it right here. I'm gonna plug in on the left side what y prime is. So the y prime just gets turned into xv prime plus v. Equals. Now on the right side, everybody see the y over x here? Y over x turns into v, right? Just v. Y over x would just be v. And then plus, now I have a square root of 16x squared minus, let's be careful, we have y squared, but I have to change that into x squared v squared, yeah? And then that's all over x. Now, if you've done this correctly, there should be no more y's in anything you've got written down here. There should be no more y's there. You guys with me? So the y prime on the left turns into xv prime plus v from here. On the right side, y over x turned into just v. I can see from right here that if I write down y over x, it will be equal to v, right? And then here, I replace the y squared with x squared and v squared. Okay, now I want to simplify this. I'm going to do a little bit of algebra and try to simplify this. I need just a little more room. Let's just do it right here, I think. Almost done, guys. Sorry, I don't normally talk this long at one stretch, but we're almost there. So does everybody see that I can cancel the V's from the left side and the right side? I'd like to do that first. It's pretty easy. And then look at this last term over there on the right with me for a second. So I've got on the left, I've got the xv prime. By the way, I'm gonna write the v prime as dv over dx. I'll write it as dv over dx because it's gonna be separable in a minute. And then in this radical that I have, you see that I have a common factor of x squared. I can factor it and then pull it out of the radical and then cancel it with the x that's on the bottom. I can do all of that. And so the right side actually just becomes the square root of 16 minus v squared. It's really cleans up quickly. It cleans up really quickly. And as promised, this is separable. This one is separable. I can get all of the x's onto one side and all of the y's onto the other side. I'm going to do that right now, guys. I'm going to divide the square root of 16 minus v squared under that dv. And I'm going to throw all of the x parts to the opposite side, which means I actually have to flip over the x and the dx so that it looks like that. This is separable. A bit of algebra there to get it separated, but that's where we're at. It does become separable. How do we solve a separable differential equation?
Integrate.
We integrate both sides. Absolutely. I'm going to throw an integral sign in front there and there. Yep. That's it. Now on the right-hand side, when I integrate 1 over x dx, everybody probably knows that one because it comes up a lot. It's the natural log of the absolute value of x. I will put a plus c on that. Okay. The one on the left is not one that most people would have right on the top of their head. You probably have seen it somewhere in your calculus class. It's
Tan
usually
inverse.
you do it using it does involve trigonometry. So you use a trig substitution for it. It's actually an arc sine. This one I would not expect you to know cold. I will give you a table of integrals or something for this one. This integral on the left is actually the arc sine of, and it's actually just v over 4 as it turns out. So the factor of 16 leads us to having a 4 there. So this is what we're ultimately going to have. And now, is that my final answer? Probably not if I'm asking the question. No, this would not be the final answer. What would you want me to do to get to a final answer?
Separate v.
Try to get the v isolated, right, to kind of pull it out. In order to do that, I got to get rid of this arc sine. I can do that by simply taking the sine of both sides. So I'll write it as v over 4 on the left equals the sine of the quantity ln of absolute x plus c. And now I'm going to throw the 4 to the other side of the equation. Like so. So just get the v by itself. And now am I done? What's wrong with this answer?
We solved for v, not
All right, this is what v is equal to, but the original problem, which is up here, is asking us to solve for y. The y is the original unknown function. So I know what v is. I have to figure out what y is, but that's an easy connection to make right here. Y is just x times whatever v was. So therefore, we can write that down. I have a little bit of space here. I'm going to squeeze it in, guys. I have to put a factor of x onto the right-hand side so that I can actually write down what y is equal to. It will be equal to 4x. Sorry for writing this so low. For those of you in the peanut gallery back there, if you want to stand up, you can't see it, feel free to do that. You end up with an extra x here, 4x times the sine of the quantity of ln of absolute x plus c. What do you guys think? Make sense? Pretty reasonable? Yes.
I'm sorry, can you explain again real quick how you got 16 minus v squared?
This one.
Yeah.
Yeah, I kind of just talked through it here. If you look at this thing right here, if you actually pull the x squared out of that, so you inside the radical, you can factor an x squared there. Well, the square root of x squared is x. So it cancels it
I see it.
and just leaves it. Yeah, does that make sense?
Yeah. thank
Yeah, so it actually cleans up really nicely. Yeah. Okay. Anything else?
Third time.
Please.
So when is it appropriate to put a G when you're
You always need the plus C. When you integrate, you always have to have a plus C on it. The only time when I didn't do that was with the integrating factors earlier, when you're just looking for one, but otherwise you should always have it there. Yeah. Okay, guys, let's take a 10-minute break. If you want to get up, go outside, stretch your legs, get some water, whatever. I have to run down to my office because I picked up the wrong roster. So I'll come back with the correct roster and we'll go through that real quick. So I'll see you guys in about 10 minutes and we'll pick things up from there. Oh, and if you have questions on the homework for tonight, feel free to write those problems on my sideboard, and then we'll come take a look at those in a few minutes. Okay.
Use action.
Do it again.
Differential equation, that is the differential equation for a superboard. Linear plus k.
Thank you.
Yeah. Yeah, the beginning is like the midpoint where it flips, right?
I'm gonna put up this problem.
Unless you want to show me something.
Yeah, honestly, it's pretty specific. So basically, because honestly, I read some checks out, but I really don't understand like what he was trying to say. Like, just in a sense that multiply entire equation by its square, and then after that, he would do left side equals the part they were doing.
It's going through the motions of it. That's one of the things changing.
Yeah, well,
So that's going through the motions of how the active action does the magic. Or is.
yeah.
They derived it also in the video. But all you actually.
That's, thank you. All right, excuse me, please.
Your Aaron. Okay, just put your initial. Yeah,
Thank you.
That's right. Awesome.
I'm gonna pass it on.
Oh, no worries.
Yeah, thank you.
Oh, no,
You don't need to work out. I just need to know which problem it is. So then I know to look at it. Thanks. Oh, no. I got it for you.
Thank you.
Sure. No worries.
Okay, guys, I'm gonna try again. I think I have the right roster this time. I just passed out the wrong page before. So I'm gonna send this around. Again, if you could just initial next to your name, if you're on this list already. I just printed this out this morning, so it's very current. If you're not on this paper anywhere, please just add yourself with your, I just need your campus-wide ID number and your name on the bottom of this third page. And then I'll do my best to see where my waiting list stands and how I'm gonna be able to, if and how I'll be able to accommodate any extra folks. So just go ahead and send that around. And once it gets all the way around, I'm gonna take a few minutes and check if I know everybody's names. Probably not yet, but I'm getting there. Okay, so we only have about 25 minutes left. My plan is to spend most of that time kind of helping you with some of the homework that's due tonight. It's kind of a way for us to practice the problems that we've just been learning about. Just gives us some extra practice, okay? And that also hopefully makes your life a little easier in terms of submitting the homework. Remember, the homework is due tonight at midnight. And if you still have more questions after class, that's fine. You just have to bring them to my office hours, okay? But let's do, a few people put some of the problems up here. So let's go ahead. I'm actually gonna start with number 2 from section 1.6. I wanna take a look at this. Here's the differential equation. dy over dx plus 2 over x times y equals 5x squared. Now, technically speaking, the first thing I would probably do is I would ask myself, is it linear? Or sorry, is it separable? I would probably, just because that's what I learned first, is it separable? Can I get all of the x's on one side and all of the y's on the other side? And I would pretty quickly convince myself that I cannot do that. I cannot move this y to the other side of the equal sign without also having to take this 2 over x over there with me, right? So it's not really possible to separate it. And furthermore, it looks exactly like the form of the linear differential equations. Actually, the real reason that you know that this is going to be linear is because it's in section 1.6 of the book, which is where we learned about linear equations. But you know that when it comes time to take an exam or a quiz or something like that later in the semester, it's not going to be staring at you saying, oh, this is from the linear equations, right? So you're going to have to be able to identify them. Yeah, so this is linear. Y prime plus p of xy equals q of x. My p of x, guys, is right here. P of x is 2 over x. And my q of x is on the right-hand side. It's got a 5x squared with it. And so what I have to do to solve this is I need to write down, so here's our little cheat sheet. The technique to solve a linear equation is to write down the integrating factor, right? So I'm going to do that here. I of x equals e to the power of the integral of p of x dx. So that would be the integral of 2 over x dx. Okay, so far so good. And now when I do the integral itself, there's a 2 here that I actually think we can just pull out into the front. And when I integrate dx over x, what do I get? The ln of x. Technically, it should be the absolute value of x, but I believe in the question it even tells you that they're just assuming that x is greater than 0. So we won't worry about that. We're also not going to worry about a plus c. On the integrating factor, you never have to do that. So you can just ignore the plus c. This is it. This is it right here for your integrating factor. But it can be cleaned up. It can be cleaned up and simplified just a little bit, right? I would love to cancel the e with the ln. In order to do that, what must I do? Properties of logarithms. What's going to happen with this 2?
squared.
It's gonna go to the exponent of that x. It becomes an x squared. That's right. So that's just equal to x squared. That's right. Okay, great. So there's my integrating factor. Now I'm gonna come back here and use this box. This box tells me that what we get is the derivative of something in brackets, which is the integrating factor of x squared times our unknown function, which is y. The other side of the equation is just q of x, which was 5x squared, times the integrating factor, which is actually another factor of x squared. And so that actually just becomes 5x to the fourth. Pretty nice. Okay. All that's left to do is to solve for y. The first thing I need to do in order to solve for y is integrate on both sides. So I'm ready to now integrate. I'm going to integrate on both sides. X squared times y equals, I have to integrate 5x to the fourth dx. What is the integral of 5x to the fourth dx? X to the
X to the fifth over 5. And then
Fifth.
5 cancel
So
out.
5 cancels that, so it's just x to the fifth, right? Would I want to leave it like that? What do I need to do to fix it? Put that plus c there. On this one, I do need the plus c. Exactly. And now I'm going to solve for y by getting rid of the x squared that's in front. So I have to take this whole thing and divide through by that x squared. Guys, this is the final answer. This is the final answer. Now, it would be okay with me. It would be okay. I like that answer the best. Okay. But I just want to point something out. If you wanted to, you could take x to the fifth divided by x squared and write it as x cubed. And then you could write this as c over x squared to like split up the two terms. That's also fine. But what is not fine is if I see people do this from time to time. What you cannot do is take this c over x squared and label it like some new constant. That does not work. You saw me do that in the videos occasionally where I would relabel a c with a c1 and then a c2. That's okay to do that as long as there's no x anywhere around. If there's an x in this expression, it's not a constant. The x is not a constant, so you can't just absorb it into the c. So I personally like the answer in my box the best. Okay? Your high school teachers probably always told you, maybe even your calculus teachers, oh, simplify, simplify, simplify. I'm not so big on that. I'm perfectly fine leaving the answer exactly in the form that you first arrived to it. Okay, so this is perfectly good. Is there any questions on that one? You okay?
Oops. How'd you get the second x squared?
So this one is coming from the q of x, and this one is coming from the I. So the I is x squared, and the q of x is 5x squared. And so what you see here is that you actually have to multiply them. So the q of x was 5x squared, the I was x squared. Yeah. So they're both going to be there. Yeah, great. Anything else? So far, so good? All right, let's look at number 12 together. I'll go ahead and do this one with you as well. Here we have x squared plus 1 times y prime plus y squared equals -1. Now, when I see the y squared on that, it's not linear, right? So the linear equation, again, if an equation is going to be linear, there's no y squared anywhere. You have to have just y and y prime. So this one is not linear. Well, and in fact, since it's from section 1.4, we actually know that it's separable. It's going to be separable. And let's try to see if we can take this equation and separate it. That's the algebra that we have to do to kind of get the x's on one side and the y's on the other side. I would probably start, guys, by rewriting the y prime and 3y over dx. And at the same time, I'm going to go ahead and subtract the y squared to the right side there. By the way, take note, there is an initial value given here. We don't do anything with that initial value until the very, very end. Until the very end, so I'm kind of ignoring that for now. Yeah, just sign in, just initial on that sign in sheet, keep that going around. Do people believe this is gonna be separable now? Can you algebraically kind of get all the x's on one side and all of the y's on the other side?
Yeah.
I think so. What's all the way over here on the right side can be divided down under the dy, right? I'm actually gonna factor out that much. I'm gonna factor out this negative, if you don't mind, so it's negative of the quantity, 1 plus y squared. And then I throw the dx to the top of the right side, and at the same time, I have to divide down the x squared plus 1 on that right side, but that is separable. Yeah, we've totally separated that guy. All of the x's are on one side, all of the y's are on the other side. Now, this is all just algebra. And I can't really give you a lecture about like, oh, well, how do you get it separated? Every problem is going to have slightly different algebra. Sometimes you'll have to factor things. Sometimes you have to do cross multiplying of things. Sometimes you might have to rationalize a denominator of something like this. Any kind of algebra could potentially show up, right? So you just have to be prepared for that. Once we get it separated, what we know is that we're going to integrate on both sides. That's the technique here. Does anybody know the integral for 1 over 1 plus x squared?
Tan inverse.
Yeah, that's the arctangent of x. So on the right-hand side, I have the arctangent or the inverse tangent of x. I'm going to put the plus c over there on that right-hand side as well. On the left side, I actually have pretty much the same thing, except there is a negative here. So there's a negative of the arctangent of y. So there's a minus sign, but otherwise, it's exactly the same thing. Okay. So far, so good?
Yeah.
Normally, what we would like to do is actually solve for y. So in order to do that, you might move the minus sign out of your way by just throwing it to the right-hand side. So I'll go ahead and move the minus sign across. And then if I want to get the y by itself, I have to apply the tangent to it. So I'm going to write that over here. Y would be equal to the tangent of everything that I see here on the right side. So the negative, so it's the tangent of the negative of the arctangent of x plus c, like that. It looks a little messy. This is one where I don't feel like you get a lot of mileage out of actually isolating the y, but technically that would be an answer. Would this be our final answer? Like, would we be done right now?
No, you have to apply the initial condition.
Correct. We are not done because we given an initial value here of y of 0 equals 1. What that means is that I technically need to plug in 0 for x and 1 for y so that I can solve for c, right? So if I put in a 1 for y, and I have tangent of the negative of the arctangent of 0 plus c on the end of that. Now, I don't expect people to be absolutely totally on top of all these trig values all the time. It's not really a big deal for this class, but the arctangent of 0 is just 0. If you take the tangent of 0, you get 0. So the inputs and outputs being flip-flop doesn't change that, right? So the arctangent of 0 is actually just 0. Like that. So we can just kind of take that as a freebie. Not a big deal. So 1 is equal to the tangent of c, basically. And now again, I have to ask you a trig question. Does anybody know what angle has a tangent value that would be equal to 1?
Pi over 4.
It is pi over 4. It's not something that you need to lose sleep over. For this class, this will not be coming up very often, but a little bit of trig knowledge never hurts. So pi over 4, that is the right answer. So what you should do now, once you actually have figured out the c value, is go back to your general solution. This one is called the general solution here. You should go back to that one and then plug in the c value to get the particular solution. So our final answer here, guys, should be y equals the tangent of negative of the arctangent of x plus pi over 4. Something like that. Doesn't look terribly pretty, but that would be a good answer. Questions there? Where's my little sign-in sheet at this point? Has it made it all the way around the room? Everybody checked it. Could you send it kind of up this last row, I think, and then I think everybody will have had a chance to sign in. Okay, and how's my time coming? I have just a little under 10 minutes. It should be good. Let me say a quick word about number 26 from this same section here. 26 is the little Sherlock Holmes mystery. And so I won't write the whole question on the board because it's a lot of words, but I'm going to kind of give you the fast version of the question, and I'll just write down just what's essential for it. It's a Newton's law of cooling problem. Now, Newton's law of cooling, I got the differential equation right here. But you actually don't need to use that. What you need to use for this practical application is not the original Newton's law of cooling differential equation, but actually the solution to that equation, which I did in the notes last week, and I'm going to write it down here. I did it by solving it as a separable differential equation. This is the $1 million equation to do this particular problem. If you solve Newton's law of cooling, you'll get this. And I went through all of that in the video that you took notes on. So it's not such a big problem. You're just using this to answer this question, which actually means that there's no calculus in this at all. There's no 250B, there's no differential equations. It's just going to be plugging numbers in to this thing to figure it out. So let me just read it briefly. At 2 p.m., the temperature of the victim, so this is a murder mystery. So somebody was murdered, and at 2 p.m. Hi, Rob. It's okay. Come on in. Absolutely. I don't want to stop you from. I don't see. Was that it?
Dead and I got office hours.
Oh no. Okay.
Thank you.
Yeah, you're welcome. No problem. Okay, so at 2 p.m., the temperature of the victim of this murder was 38 degrees, I believe, right? And then at 3 p.m., the temperature had dropped to 36 degrees. And the outside temperature is 34 degrees. So they gave us all of that information. Isn't that convenient? They gave us 3 pieces of information, and there happens to be 3 constants that are sort of to be solved for in the equation. So you're just really going to try to use this information to plug into there. It's mostly just an algebra problem. So the 34 degrees, guys, that's the T sub m. That's no problem. That's just the T sub m. You do have to decide this little t is that, I'll grab that from you in a second. The little t is the time, and you can decide in advance whether you want to measure the time in minutes or seconds or hours. In this problem, because we're talking about 2 p.m. and 3 p.m. and 10 a.m., hours would be a good choice, but you technically don't have to choose hours. But let's measure the time in hours, and we have to figure out when are we starting our clock, like when is t equal to 0. There is no right or wrong answer for that. You can pick any starting time that you would like, but I will tell you that for the numbers to come out the easiest, you should choose t equal to 0 to be at 2 p.m. And if you do that, then of course 3 p.m. becomes t equal to 1. And you can use those values to help you solve for these constants. So I know it looks a little intimidating at first, but it's actually a very elementary problem. We know that the temperature of the medium is 34, right? If I plug in 0 into this box, if I plug in 0 for t into this expression, I'm going to get 34 plus C2 times e to the 0. Well, e to the 0 is just 1. So you just get 34 plus C2 times 1 equals 38. Because that's the temperature at time 0. I know I'm going a little fast, but this is super just plugging numbers in and solving. So 34 plus C2 equals 38. So C2 is equal to 4. Got that number now, right? And then I've got to figure out, well, at time 1, which is 3 p.m. At 3 p.m., I've got 36 degrees. So this is 34 plus C2, which is 4, e to the negative k times 1 is equal to 36. So at 3 p.m., the temperature should be 36. And if you finagle that around, 34 subtracted from 36 is 2. Then you divide by 4, you get 1/2. So it's just e to the negative k equals 1/2. Take the ln of both sides of that, guys, and you're going to get your k value, basically. So if I take the ln of both sides, the ln of e to the negative k is just negative k. And that equals ln of 1/2. So what you're going to want to do then is come plug all those numbers into here, right? So the temperature, it becomes 34 plus 4 times e to the negative k part is the ln of 1/2 times t, like so. You just put that in there, and this becomes your equation. And now all you're going to do is say, they say, is the time of death 10 a.m.? So you can plug in -4 hours, because -4 hours, if I go 4 hours before 2 p.m., that would be 10 a.m., right? So 4 hours in reverse. Guys, you will need a calculator here. Just take a calculator, plug in -4 for T, and see what the temperature is. The normal body temperature is supposed to be 98 degrees. So you should be able to plug in -4 for T right here. Simplify that with a calculation, and you should get 98. The answer is yes, it does work out. Does that make a little bit of sense? So it's mostly not a serious calculus problem. Okay, I'm basically out of time, but I need to steal just a minute to go through my roster really fast. I'm going to do this really quick, and I'm going to call out your names and just say here if you're here. And if you need to correct my pronunciation, you can do that too. Is Charlize here? Charlize, thank you. Gabriel. Gotcha, Gabriel, thank you. Janalee. Anthony Benitez. Thank you, Anthony. Adrian. Thanks, Adrian. Aiden. Got it, thanks. Aaron. Oh, Aaron's not here. Oscar. Gotcha. Oscar Korea. That's okay. Caesar. And Joel is here. Brandon. Thanks, Brandon. Rushdie. Did I say that right? Rushdie. Gotcha. Thank you. Christian. Thank you. Hayden. Thanks, Hayden. Oscar. Got it. Appreciate it. Stephen. Thanks, Stephen. Dale. Thanks, Dale. Safa. Thank you, Safa. Dari. Thank you. Jasmine. Great. Arnav. Am I saying that right?
Yeah.
Arnav. Okay, great. Thank you, Arnav. Kim. Thanks, Kim. Josh. Is Josh here? Josh Robles. There you are. Thanks, Josh. Raphael. Got it. Bishoy. Am I saying that right? Bishoy. Okay, thank you so much. Cody. Thanks, Cody. Dylan. Thank you. Nung. Thanks, Nung. Jordan.
Here, thank you.
Thank you. Brian. Thanks, Brian. Aaron.
Here.
Thank you, Aaron. Yar. Got it. Eric. Thanks, Eric. And Griffin. Got it. Perfect. Jasmine and George, can you guys come up here for just a second? Just want to check in with you real quick.